What's up, guys? Welcome to episode number 4 of Benzene Chemistry. In this episode, we'll go through Nazarov cyclization, which is a way to transform a divinyl ketone into a cyclopentenone. As usual, we'll go through the reaction mechanism, then we'll check out some literature examples, and finish up with some exercises. In Nazarov cyclization, you want to transform a divinyl ketone, like this example, into a cyclopentenone using a Lewis acid, or it could be a regular Browder acid, but most of the time a Lewis acid is used. So your divinyl ketone is this. You have two double bonds next to your ketone, and with two different R substituents that will impact what you get in the end. And you can have some substituents here and here too, which will influence as well. So let's see the reaction mechanism with a Lewis acid. It's very similar with the Browder. I'll just show you the differences as I go through it. So what you want to create in this reaction or form is this bond between those two carbons, and keep one of the alkenes there. Sorry, here. So it starts off with your oxygen attacking your Lewis acid. Then you get this intermediate, which you can see can be stabilized by the two adjacent alkene. This is called a pentadienyl cation. So it has these resonance forms. So the positive charge can be either here, on this carbon also, if this goes here and this is not stabilizing, and on the oxygen itself. Usually it's represented like this, pentadienyl cation. Alright, so we know that either A or B will be the resonance form that will lead to our fifth bond here between the two carbons, because this one won't be making it. So let's check out what if we have either A or B. So if we have A, the positive charge is on the right side, and the alkene will attack this carbon to create this magenta bond. If this stabilizes the positive charge, then you get this molecule with the cation on the right side. And you can notice that if you started with B as your resonance form and attacked from the right side to the left side cation, you get this. So these two are equivalent and are in resonance, so it doesn't matter. But in some examples, they tweaked their starting product so that one of the alkenes was more likely to have positive charge on it, and the other one was more electron rich and would be the one that attacks most of the time. You can go check this out in the review that I'll post in the description. So if you have either one of those, you can eliminate one of the protons, or it will spontaneously eliminate to stabilize the positive charge. So you get this second bond that you just formed, either the orange one or the yellow one. And now this is with the version that you have a Lewis acid. If you would have used the Browder acid, this is only called isomerization. So you get your keto-enol equilibrium, which is highly favoring your ketone. But in this case, you can just push these arrows, and your Lewis acid leaves. It was all right in the beginning. It can just leave, give the electrons back to form the ketone, and your alkene will attack any hydrogen in the media. So you get your new double bond, carbon oxygen double bond, and you get your hydrogen here. One can notice that you lose a stereocenter. We'll talk a lot about that. But yeah, depending on which one has the alkene, you lose your stereocenter. So it's not sp3 anymore, it's sp2. So in this case this one, in this case this one. Just to be more specific, during this elimination, what actually grabs the hydrogen would be your counter anion that you just released from attacking your Lewis acid. In the case of a titanium tetrachloride, you could release a chloride atom that will eliminate, hence forming HCl. So that's where your hydrogen comes from, and this is why it can form back the ketone. Because I was wondering at first, where was the hydrogen coming from? So that's from the elimination. And you encounter an ion in the media that you just created. When your positive charge was delocalized on 5 carbons from 2 alkenes, I said it was a pentadienyl cation. When it's on 3 by 1 alkene and your oxygen in the middle, it's called an oxalate cation. So let's see how this bond, the green one or the magenta one here, is formed in details. So in the last episode, if you guys watched it, about Curry-Fox reaction, I mentioned when I talked about the carbene rearrangement, or how the carbene function in the mechanism, I mentioned the Woodward Hoffmann rule. And this one is particularly important, and it's about the conservation of orbital symmetry during the reaction for pericyclic reactions, which are reactions which have a cyclic transition state. Just like this one, because you see the transition state is when you form this 5th bond to create your 5-membered cycle. So here I am, zoomed in, here to explain you guys what this is about. So we're going to be looking at the bond formation, and we need to know what set of p orbitals are involved to create this bond, because you know that it's an alkene that attacks an empty p orbital to create your 5-membered cycle. So you have to check out the symmetry of the p orbitals involved in this bond formation. So I went and found this in reference Symmetry, and according to the Woodward Hoffmann rule, you have to place, in this case, your 4 pi electrons somewhere. So there are 5 atomic orbitals, or 5 energy levels that you can visualize, and you get n-1 nodes in them. So the first one would be this, with the same signs on the same sides for all 5 carbons. This is 5 carbons. But this is not interesting because it's not either the HOMO or the LUMO or the SOMO. So what we need to look into is your HOMO, because this is your set of p orbital that will react. So if you're in thermal conditions, so normal conditions, you just heat it or cool it down or whatever. According to the Woodward Hoffmann rule, for 4 pi electrons, you'd be in con-rotatory movement. And according to the same Woodward Hoffmann rule, if you'd be in photochemical conditions, so if you'd send a beam of light with a particular wavelength to excite your electrons, you could excite them to a superior energy level, which would put them in this SOMO. You would be concerned about this SOMO. But in our case, in the Nazarov cyclization, you're in thermal condition, so you're in con-rotatory movement, and this is our HOMO that we're concerned with. So we have the 2 first carbon that have this set of p orbital, and a node in the middle on the 3rd carbon, the one that has the oxygen, and the 4th and the 5th carbon are at opposite signs. So this dictates that we'll be in a con-rotatory movement in order to keep the orbital symmetry during the transition state. So as I said in the last part, you either have a con-rotatory mechanism, con-rotatory, or a disrotatory. Con-rotatory means that both of the p orbitals involved in your bond formation are going in the same rotational direction, so either both clockwise or both counterclockwise. And disrotatory is the opposite, so they move either towards each other or away from each other in opposite directions. So in this case, in the Nazarov cyclization, we either have a clockwise or a counterclockwise, because we're in a con-rotatory types of movement. So like I've shown in the yellow arrows here, you can rotate around these bonds and in a clockwise fashion, so that both p orbitals involved meet with the same signs in order to keep the orbital symmetry, like the Woodward Hoffmann rule stipulates. So you get this. So your R substituent moves upwards and this one moves downwards because they're both going clockwise. So in this case, you get your R substituent upwards, this one downwards. And you get your oxalide cation, which I talked about. And it can delocalize, so you get this. The positive charge is between these three carbons. And if you're going counterclockwise, the same thing happens, but counterclockwise. So you rotate again around these bonds, and the R prime substituent, this one goes up and this one goes down. So this one is downwards and this one's upwards. So you get these two different oxalyl cations. Let me correct this real quick again. This is actually your darker, not white part that's creating the bond. Because if you're turning counterclockwise, like I said, this goes down, this goes up. So the parts that meet with similar polarities are the ones that are not white in this case. So sorry for that copy paste. So in the end, you get these two oxalyl cations, oxalyl again, and in this case you get enantiomers because they're mirror images of each other. And there's a certain type of selectivity that describes how that you prefer either going clockwise or counterclockwise depending on your starting molecule. So it can be because of steric hindrance, for example, but sometimes this bond formation occurs only or most of the time in a clockwise fashion. So the counterclockwise way is not favored because you get steric hindrance or something. So this is called torquoselectivity, and we'll review an example selectivity, and we'll review an example of it in the literature examples. And another thing, generally in the end, if you have the chance to form, because I said you get either this one or this one, if you have the chance to form a more substituted alkene, then it will be favored in the end. So the more substituted alkene is favored. It's a major product. So that's it for the reaction mechanism. I hope I didn't say anything too wrong. These are new concepts for me that I explore during these literature reviews. So let's see the synthetic uses for Nazarov's reaction. So you lose a stereocenter during the elimination. So when you pass from your oxalyl cation to your final molecule, if you let it go through the normal Nazarov cyclization, then you lose the carbon that is now sp2. Either this one or this one. You lose the steric information and you keep the other one. So one way to avoid that is to trap the oxalyl cation. So in this fifth reference, you start with your divinyl ketone, and you have an alkene that's tethered to it, one of the R substituents. And by reacting it with the Lewis acid, which in this case is this one, you get your normal oxalyl cation like you would expect. You form this bond, and now this alkene can attack your oxalyl cation to stabilize it and to form another cycle. In this case it attacked from downwards because you see the methyl is now upwards. And now you have this tertiary cation here. And your oxygen can attack it once more, lose the Lewis acid, and form another cycle. And now you have your alkene here. If you hydrate it, you quench it with water, then you get this OH here, and you've created 3 cycles. And this is called an interrupted Nazarov, because you see you kept the stereocenters here and here, and you did not lose it, but you did not form the final alkene. So this is a way to keep both of your stereocenters and to interrupt your Nazarov reaction. and this was by having your alkene on one of your R substituents. Alright, so a second version of an interrupted Nazarov reaction is this one, where they also had an alkene as an R substituent, and as their Lewis acid they used titanium tetrachloride, and it's a strong Lewis acid since titanium is +4, and it's not saturated because it only has 8 electrons in this case, plus those from the titanium, and it's not at the 18 electrons that the transition metals tend to want. So it's a strong Lewis acid, and the oxygen attacks it. And you get this, and then you get your oxalate cation, because this bond happened like we saw. You had your pentadienyl cation, which got attacked. You get this, and then your alkene can attack, like we just saw, and give this intermediate. And now they had many routes which they explored, and let's see them through. So the first one was that they trap it with chloride, coming from the titanium chloride, and they only use this Lewis acid because they sometimes use combos of 2 Lewis acids, and yeah, so the positive charge on this carbon got attacked from a chloride, and it got attacked from either side, so this is not a clear stereochemistry, but the ratios is 1 for 12 for 35, and 12 being the normal elimination, and 1 being where the elimination occurred where the positive charge was. So either of these hydrogens here, there's 2 here, or here, or here, got eliminated, so they got this elimination product. In the case where they only use titanium tetrachloride, this is a ratio. They could make this one preferably by using a combo or combination of boron trifluoride and titanium tetrachloride, and they got mostly this. And other case that they explored was that by using only boron trifluoride, they got this. They got a 3+2 cycloaddition. So they got this intermediate, and then the alkene attacked this and formed another cycle. They got this molecule. And the last route that they explored was with using a combo of BF3 and PiCl4, and in this case they switched the conditions and got a hydride shift. So if you see it this way, this hydrogen could shift and go there to stabilize the cation, because now it's next to the alkene, which can stabilize it. So now you get this. So you had your hydride shift, which came from downwards, so you get only this one. Alright, so for the third literature example, these are the references. These guys explored the torquoselectivity aspect of Nazarov cyclization. So like I said, we're in thermal condition, so we're in con-rotatory movements. So it's either clockwise or counterclockwise. And when you have 2 substituents on one side, you eliminate in a way to produce a more substituted alkene. So the one stereocenter that you keep is the one, in this case, on the right side. So if you go clockwise, you get this R3 substituent behind the cycle, and if you go counterclockwise, you get it coming from the top. Quick correction, I noticed that, or someone made me notice that I misnamed these R substituents. If I don't want to keep the same notation here, it would be R4 here and here, 1, 2. This is 1, 2, 4, 1, 2, 4, and 4. Sorry about that. And how one way is favored over the other is called torquoselectivity. So if the clockwise rotation is favored over the counterclockwise, then you get mostly of this one, and you get this as your minor product. So in this example, they explored it with this reaction, and they used R for their R prime substituents silyl group with different bulkiness. And this silyl group ensures that you get your alkene on one side of your molecule. In this side, you get your alkene here, because you can't get it here because you already have a proton. So what varies really is this is the stereocenter that you form during your cyclization, because it impacts your R substituent. And what they found was that the larger the alkyl group, the better the selectivity is, and the bulkier the silyl group is, you get more selectivity, but you reduce your yield. As you can see here, with this very bulky R prime group, they got 70%, and with this rather small one, they got 99%. But they increased the selectivity for the A product, which in this case would be the counterclockwise. And I wasn't sure, so I went up and did them in Chem 3D. And when it optimized, maybe I can zoom in. Okay. So this one would be this. So you see your chair here. And you got your R group that's going upwards. And your hydrogen rather, is here. So you got both of them going upwards. And you got your cycle there. And this one, with your R going downwards. So there it is. This is your R, and this one is your H again. So this is depending on when you approach your p orbitals. Did you do it in a clockwise or counterclockwise fashion? And this can be explained by looking up the starting molecule, which is this, which I also did in Chem 3D. So it's this molecule. Alright, so this is a cyclohexene. So if you remember, this cannot be drawn as a chair conformation. It can be something like this, or a boat, like Chem 3D showed me. Or an envelope, rather. This. And your R substituent is upwards. So if you rotate around this bond, the one holding the carbon that has the oxygen, then you can bring your the rest of your molecule this way. And when they react, they either go clockwise or counterclockwise. But since the silyl group is bulky, it prefers going either clockwise or counterclockwise in a way to avoid the R group. This is because of steric hindrance. So in this case, if you look up their ratio that they got, I think the one that's going counterclockwise based on the starting molecule yields A, and the one going clockwise yields B. So the one going counterclockwise allows to have the less negative steric hindrance happening, so you get this major product, which is A. And that's why they tried to exploit by varying the torquoselectivity, by varying the bulkiness of this R group and this silyl group. And they also forced the orientation of their alkene, so to keep this stereocenter. Quickly before going to the exercise, I just wanted to mention that this carbon-silicon bond is pretty weak and so long that that's why you only see it on this side, because it doesn't need much to give back these electrons and to stabilize your positive charge there. So it just needs a halogen, and then you can kick it and create your pi bond. Alright, so that sums it up for the third literature example. Very cool reaction. I reviewed just a bit of it. You guys go and look up the literature review, which is reference number 4. There's a bunch of them. recent advances in the Nazarov cyclization, you can look it up. So let's jump into a quick series of exercises, 2 of them to be precise. So in both cases, you start with a divinyl ketone. What differs is this carbon, which I just erased. This carbon, this one is cis, because this is a cis alkene, and this one is trans. So what are the 4 products that you get? So these are the answers. What if you go clockwise, you get this green one, and counterclockwise, you get the red ones. So it was a trick question because you lose the steric information on your left side carbon because the alkene forms on the left side because it's the most substituted since you have your methyl there. So in both cases, you get the same products. Alright, so that's it for Nazarov cyclization. Thanks for watching. If you've made it to the end of the video, you're really one of a kind. Please feel free to leave comments, to like and subscribe, and watch the other 2 videos that are the previous ones. As usual, the references are in the description below. Like I said, these were new concepts to me, so I might have passed or overlooked some aspects that you found was very important. Please leave them in the comments. I'll be very happy to hear them, and I'm very eager to learn this in school. So that's it. See you guys in the next one.